So today we're starting Unit 5. Unit 5 is called Mutually Exclusive Events. So what we're going to be looking at is two or more events happening. Now this does change probability. The first bit that we're going to look at is what's called multiplication rules, because when we deal with mutually exclusive events, we will be multiplying. So there are two types of events that we could have when talking about mutually exclusive. You will also hear to us refer to it as your AND probabilities. The first type is called independent. Independent probabilities are where one event happening or not happening does not change the probability of a second event. For example, we could be pulling a card from a deck, and then we put the card back. We started with 52 cards in the deck. After we pulled it, we put it back, so we still have 52 cards. If we had a bag of marbles, I could pull one out and then put the marble back. That makes it independent. The other type is called dependent probability, where one event happening or not happening changes the probability of the second event. Talking back about that card, if I pull from a deck of cards, well, in a deck of cards there's 52 cards total, I pull a card out and I set it down, well, I don't have 52 cards anymore, I have 51. That changes our probability. So we actually have a very nice formula for either independent or dependent probabilities. And that is probability of event A and B is the same thing as probability of event A times the probability of event B. So AND means to multiply. However, we sometimes have this weird condition called a conditional. A conditional event adds on a condition, which is why we call it conditional. Now, that condition would be as simple as, well, instead of looking at all of the students at West, now we're only going to be looking at males. Instead of looking at all of the cards in a deck of cards, we're only looking at the red. So what the conditional probability does is it adds a catch. It changes the total that we're going to look at. And the probability to find an AND where one of them is a conditional is literally the same thing. We're still multiplying. However, I do want to point out this right here is how we know it's conditional. Probability of event and then that vertical line, B. That vertical line is pronounced given. So if we read that, it literally says probability of event A given B. And if we ever need to find a conditional probability, we're going to take the AND, so the probability of event A and B, divided by the probability of B. Now we know it's divided by the probability of B because in the given it says probability of A given B. So that's how we know to divide by B. If it was flipped and said probability of B given A, well, we still are going to multiply for the top probability of A and B, but this time we're going to divide by the probability of A because it's given A. We'll look at some of these later on. So example 1, suppose you're going to throw 2 fair dice. Well, what is the probability of getting a 5 on each die? Now, because we're rolling 2 dice, I know that this is going to be independent because the first dice, no matter what it is, does not affect the outcome of the second die. So the probability of getting a 5 on the first die, well, there's 1 5 out of 6 options, times, well, for the second die, same thing. There's, on the second die, 1 5 out of 6 options. Now to multiply fractions, we multiply across. So top times top, bottom times bottom. So 1 times 1 gets us 1. 6 times 6 gets us 36. Looking at the second one, probability of getting an even number and a 7. Well, an even number, well, on a die, there's 2, 4, and 6. So there's 3 options out of our 6. Times, now we want a 7. Well, there are no 7s. So 0 out of 6. Multiplying across, 3 times 0 is 0. 6 times 6 is 36. So we have a 0 out of 36 chance, or you could just say 0. Because 0 divided by anything is just 0. And then, what is the probability of getting a multiple of 2 and a multiple of 3? So multiples of 2. Well, we have a 2, a 4, and a 6. So that would be 3 out of 6 times multiple of 3. So it'd be 3, 6, 9, so on and so forth. But on a die, it's only 3 and 6. So 2 out of 6. Multiply across, you get 6 out of 36. Example 2. Your vehicle has a 75% chance to start when it's cold out. If it does not start the first time, you try again, which is successful 85% of the time. So it wants to know what is the probability that the first try is unsuccessful and the second try is successful. So now we need to think a little bit. It says your vehicle has a 75% chance to start. We don't want it to start, so if it has a 75% chance to start, the complement would be 25% to not start. So 25% times, and we want it to start the second time, so times 85%. Multiplying, we get, well, it's hard to multiply percents. So what we're going to do is convert them to a decimal. To convert a percent to a decimal, remember, we divide by 100. So this would be 0.25 times 0.85. Now we can actually multiply. Multiplying across, we get, or not multiplying across, just multiplying, we get 0.2125, or 21.25% chance that this would happen. So we have a little did you know, and this did you know is going to be very important. It says in order to prove 2 events are independent, meaning, remember, one does not affect the other, this has to be true. The probability of event A has to be equal to the probability of event A given B. Both of those have to be true. Now, when we deal with probabilities, we've always dealt with them as a fraction. Well, it's hard to compare fractions with different denominators or different bottoms. So we're probably going to have to, for comparison's sake, put them as a decimal. So looking at example 3, says students are sorted, as I misspelled sorted, randomly into 4 houses at a certain school seen below. So A wants us to know the probability of event A, so being sorted into house A. So how many total people were in A? 124. Out of how many total? 350. And now we have a conditional, in our first conditional. It says probability of A given they're a boy. So the only thing, because of that conditional, only thing we care about is the boys. So how many boys then are in house A? Well, 75. Out of our total boys, 162. Now, like I said, it's really hard to compare fractions. So let's convert them to decimals so that way they look nicer. So 124 divided by 350 gets us roughly 0.35. And 75 divided by 162 roughly gets us 0.60. So now we can actually answer this question C. Determine if the class you get sorted into is dependent of gender. Well, in order for it to be independent, that had to be true. So because those two are not equal, we can say these are dependent. And as an explanation, we can say, well, 0.35 is not equal to 0.6. Example 4. Example 4, a marble problem. So in a bag, our bag contains marbles of various colors. In it, there are 3 blue, 5 red, 2 green, 6 yellow, and 4 purple marbles. After pulling a marble, you decide to put it back in the bag. So I already know that we already need a total. So we add up 3 plus 5 plus 2 plus 6 plus 4. We get a total of 20 marbles. I'm just going to put that off to the side for now. A, probability of blue and green. So, and once again means to multiply. So probability of blue, well, there are 3 blue out of 20. Times, we put the marble back, so there's still 20. Green, 2 green out of the 20 total. Multiply across, we get 6 out of 400. Probability of yellow and red. Well, there are 6 yellow out of the 20. And means to multiply. Red. There are 5 red out of 20. Multiply across, we get 30 out of 400. Go ahead and pause the video and try C and D. In C, it says green and red. So there are 2 green out of 20, and there are 5 red out of 20. Multiply across, 10 out of 400. Blue and blue. Well, there are 3 blue out of the 20 times another 3 blue out of the 20 equals 9 out of 400. And then E, where the previous probability is dependent or independent. And how do we know? Well, because it flat out said after pulling the marble, we put it back. That did not change our second probability, so we can say these are independent. They're independent, we put the marble back. Okay, let's look at example 5. Example 5. A bag contains marbles of various colors, so another marble. In it, there are 3 blue, 5 red, 2 green, 6 yellow, and 4 purple marbles. This is pretty much the same setup as last time, except now it says, after pulling a marble, you decide to put it off to the side. So we're not putting it right back in the bag. So that actually does change a few things. So blue and green. Well, there are 3 blue out of the 20. We pulled that, but we no longer have that 1 blue marble in the bag. It's off to the side. So there aren't 20 marbles in the bag anymore. There are 2 green, but now there are 19 marbles in the bag. Multiply across, it's 6 out of 380. Let's look at B. It says yellow and red. So there are 6 yellow out of the 20. But we put that yellow marble off to the side. There are 5 red, but it's now out of 19. And still needs to multiply. So 6 times 5 is still 30. And 20 times 19 is 380. Go ahead and take a moment, pause the video, try C and D. For C, it says green and red. Well, there are 2 green out of the 20. Times red, well, there are 5 red out of 19. Multiply across, we get 10 out of 380. Now for the tricky one, a blue and a blue. Well, first blue, there's 3 out of the 20. Times, well, we put that blue off to the side. So there aren't 3 blue in the bag anymore. There's actually only 2 blue in the bag out of the 19. So it should be 6 out of 380. So we can answer this question. Were the previous probabilities dependent or independent? Well, we put the marble off to the side. That changed our probabilities. So because of that, this is dependent. And we know that is, well, we didn't put the marble back. Last two sets. Example 6. Following table shows student population at a certain high school. I give a table. Except, unlike the first table we looked at, we don't give you totals. So here's the thing. Be prepared from now on, whenever you get a table, to not have your totals. So we're going to need to know the total number of freshmen, sophomore, juniors, seniors, total of male, female, and we need our grand total. So if we add up all of the males, 182 plus 193 plus 174 plus 201, we should get 750. Adding up all the females, so 183 plus 172 plus 184 plus 207 should get us 746. And now just add all the columns. Take a moment and do so. All right. Go ahead, pause the video, see what you can do for problems A, B, and C. So for problem A, probability of junior, well, there are 358 juniors out of 1,496 total people. Probability of junior given female. Well, we're only looking at the female row. There's 184 juniors that are female out of the 746. And then C, determine if the grade level a student is in is dependent or independent of gender. Well, once again, those two probabilities have to be equal. So, if we get them as a decimal, we roughly get for the first one 0.2393. Second one, we roughly get 0.2466. So because those are not the same, it is dependent. And we know this because the probability of junior does not equal probability of junior given female. And last example, example 7. The spinner is spun multiple times, and we have this particular spinner. So probability of green and a green. Well, there is one green section out of the 6. Times green, well, there's still one green section out of 6. Equals 1 out of 36. Take a moment, try B and C. Now, B is a little bit trickier only because it's not just 2 events, it's more than 2. So purple, there's one purple out of 6. There's one red out of 6. And there's one blue out of 6. Rule of multiplying is still the same. 1 times 1 times 1 gets us, well, 1. 6 times 6 times 6 gets us 216. So now we have that question, is each spin independent or dependent? Well, we can't really deal with the conditional probability for this problem because there's really no way to do a conditional. We never asked for one. So thinking back about the original definition of independent-dependent, independent said the first event does not affect the second event. And in the dependent, it does. Well, because it's a 1/6 times 1/6, the first spin didn't affect the next, we can say these are independent. You can say it's independent. The first spin does not affect the next.